I see a problem. Digital outputs. This is my CNC router. It has a high quality Chinese control system on it. I want to give it the power of penguins. Mechanically, I've always been really happy with this machine. It can do heavy cuts, it can do precise cuts, but the control system just isn't configurable enough to do some of the things I want to do with it. The first thing we're going to need to do is get into the control box and take a closer look at what's going on in there. Of course, I had to mount the control panel where you can't open it without disassembling the machine, and hold the cover on with an excessive quantity of poorly aligned screws. Now that we have the box open, we can see there's quite a few parts in here, but the only thing we really care about is the RichAuto controller over here on the right side. We're going to be replacing that with this, a Mesa I/O card. I went and removed one of the cables that goes from the RichAuto controls to the servo, and we need to figure out how we're going to connect that to the Mesa board. We need to know which pin has which signal, but the wire is only labeled by wire color in Chinese. I have a wiring diagram for a RichAuto controller and a manual to the servo drive, but I think the safest thing to do is going to be open up the servo end of the cable and just see how it's actually wired. So we'll pull this connector apart. So I see a problem. How many wires do you count in there? Because I can tell you it's not 15. My plan was to take one of these DB15 to ferruled wire adapter cables and just plug them into each other and be able to just wire up the ferrules to the board. But if the cable doesn't have all the wires I want to use, we're going to have to go to plan B. I ordered 3 connectors, then 3 shells, $80 delivered. But the other option was to disassemble the existing cables, and I'm still not convinced I'm going to pull this off, so I don't want to be destroying any of the existing harnessing or parts, so I could put it back together with the old controls if I have to. I'll save you the pain of listening to me mumble while I reverse engineer this cable. There's links in the description to a GitHub repo that includes all the final configurations and what notes on all the wiring and all of this. So if you're interested, you can go take a look at that. The most important thing is I figured out how we need to wire a new cable, and I went ahead and started making one of those. And I just happen to have a supply of twisted pair cable. Might look a little bit like Ethernet cable, but now it's just some 4 twisted pair cable. So we do need to get a total of 15 wires off of this, so we're going to use two lengths of this for each connector, but that's not going to be an issue. I'm going to give ourselves a little bit of extra room here because I'm not exactly sure how everything's going to be mounted, so we'll deal with the other end once we're getting things installed. I do own a real Ethernet stripper, but I can't find it, so we're just going to do this. And looks like I did not nick anything, so that'll work. Once it starts to tear, you can just sort of wiggle it and it'll tear the rest of the way around. And this little bit longer piece, you can just sort of work that off and it'll come off. Don't cut yourself with your wire stripper. Going to snip off this divider that keeps the twisted pairs separated in Ethernet cable. That's just going to get in our way. After that, assembling the connector is pretty straightforward. Strip each wire, tin each solder cup, tin each of the wires, then stick the wire into the solder cup with a little bit of heat. Do that 15 times and you've got a cable ready for some testing. The board needs 5-volt power, which we don't have, so we need to get 24-volt power from here into this, 5-volt over here, plug in our beautiful wire, and connect a couple of these back over to this board. Luckily, we don't need to hook everything up all at once and hope it works. We're going to take the step and direction signals first. Each time the controller pulses the step signal, that tells the servo to move the machine 1/1000th of a millimeter. And then the direction pin tells it to move right or left. But before we can actually test anything here, we're going to need a PC running LinuxCNC. Now we got to figure out how to get into this thing. Maybe just pop that off. That'd be nice. I guess we're taking these screws out. There we go. Stick that in. This goes on the SSD side. Oh, it also says front, towards the front. I hit a couple small mistakes during the install. The USB 3 port on front didn't work until I updated the kernel later, and the Wi-Fi needed a proprietary firmware blob that wasn't included in the default image, so I had to add that to the flash drive before I could get through the install. But after those couple hiccups, it booted up good, and we're ready to start configuring LinuxCNC. I got the computer set up to communicate with the Mesa board over Ethernet, which there was a little detour here with a slightly buggy Ethernet adapter and needing to do some BIOS updates, but I'm not going to go into that. Then we needed to do a latency test. This is basically making sure the PC can run consistently enough that it's not going to make the machine stutter when you open Firefox or have OBS running in the background. To begin with, I had some pretty marginal jitter numbers. They probably would have been fine with an Ethernet card, but disabling HD audio in the BIOS made my numbers much better, and I have no reason for audio on this machine, so we're going to leave it that way. The LinuxCNC forums are pretty good, and there's an old thread talking about how to set up the 7995T. It pointed to the Mesa configuration tool, which, as it sounds like, it is a tool for configuring LinuxCNC to use Mesa boards. Mesa CT has a button to set up a single-axis configuration for a 7995T. So I went ahead and did that, set the IP address for it to connect to. Helps if you turn on the board. Flashed a firmware. It doesn't really matter which one at this point because they all have step and direction outputs. Then we can set a couple of UI settings. And then the axis, we need to set the scale, which is how many steps per millimeter, the width of that axis, and the maximum speed. Then we should be good to open up that configuration and give it a test. Nothing's happening. So I just was looking, and right here it says pin 1. But we're connected to the wrong axis. So I think if we just do this, we might get some motion. It moves! With just the step and direction signals hooked up, the servo will get to the right position at about the right speed, but that doesn't always happen perfectly. With the encoder output from the servo to the controller can know what's actually happening and compensate for it. The forum saves us again because Tommy Light posted a configuration for a big plasma machine that was using the same card and had encoders set up on it. I put the configurations for that side by side with the ones from Mesa CT, then found the portion that was enabling the encoder and copied that over to my configuration. Then it's just a matter of using HAL meter, which is basically a multimeter for LinuxCNC's internal state, to inspect the encoder and make sure it's counting correctly. At this point, LinuxCNC isn't using the data from the encoder to improve anything, but we know it's working, so we can keep going and come back to that once the rest of the machine is set up. I tackled the next three signals all at once. The active alarm output from the servo to the controller was no issue. Hooked up the ground wire for the inputs and outputs on the Mesa board, then connected the output from the servo to the input on the board. That worked just fine, but I don't actually have any video of that. Then I continued on to the enable signal, which is supposed to turn the servo on and off. But you might have noticed the servo's been running without an enable signal. So I dug through the manual on the servo and found there's a diagnostic page that shows the status of all the digital inputs. The very upper right corner there is the servo on signal. And it's stuck on. Now, I dug into the manual. I found that if we go into one of the settings, PD01, and this fourth digit is a 1, it actually means it's ignoring that input completely. So we're going to set that, and doesn't look like anything happened. There are 4 different ways you can wire the digital inputs on the servo. I knew what I was trying to do, but I accidentally followed the wrong diagram when I made that cable. I also left a blob of solder across 2 of the solder cups. But after I resolved that, everything worked. Unfortunately, I lost the video of doing that, so you'll just have to take my word for it. But you can see that after I did that, I could touch the wire to a ground, and the servo's responding correctly. We're taking a little detour, because this is the second time I've knocked this power strip off the back of this cabinet and unplugged the PC. Future disaster averted, it was time to make room for the permanent install. I removed the cabling to the A-axis for the rotary table, which I don't have, so we don't need that at all. Then the RichAuto controller itself. This harness worked to get the X-axis moving, but we got a couple problems with it I want to address. The biggest one is I'm not happy with how these wires are kinking as they come out of the axis, the vinyl shielding. We need to secure the vinyl so all the stress of this getting to the servo isn't going on the little tiny wires. And there's really nowhere good to clamp that in the machine. What do you do when you need a weird custom part? Magic of 3D printing. 2 of these should clip on here, and we'll be able to run the wires through that loop. The next thing to do is start making 3 servo cables by using the new wiring diagram so the inputs and outputs work correctly. Really the only thing I did much different is make some nice labels so I don't have to use that paint pen on the cable. Assembling the wires went just about like the first time. I did end up breaking out the leaded solder. I usually use lead-free, but I had some issues with the insulation shrinking back on the first cable. So I broke it. You see, it's an ancient roll of Radio Shack branded cable. Yeah, that's been around for a few years. But just like before, tin the wire, tin the cup, stick them together, and then fight with getting the shell back on. You'll have to imagine this 2 more times because I only filmed the first of them. But I'm really happy with how these turned out. They're just a lot tidier than the first one. While we're cleaning things up, I'm going to reroute the power cable. I'm still running it underneath the board along the DIN rail mounts for the Mesa board, but it got left a little long. Any stranded wires from here on, I'm going to be crimping a ferrule on the end. Hopefully that will mitigate any failures from wires vibrating. I connected the common of each digital output to each other, and then tied that to an unused ground on one of the step and direction outputs. All the servos are going to share enable and clear alarm signals because I don't have enough isolated outputs on the Mesa board to give them each their own. So we've got green for go and red for stop alarms. I don't know, analogy is breaking down here. And it's time for another time lapse over tedious wiring. So I'm starting at the end of the board by the wires, connecting in the enable and clear alarm signals, the alarm status output from the servo, the step and direction outputs to the servo, and then the encoder inputs. You might notice I'm putting some heat shrink labels, same label maker, it's awesome, on each of the pairs so I can tell what these are when I come back to look at this thing in a year or two and have no idea what I did. Just a couple of zip ties to make it look a little cleaner. So we have a temporary power connection going into the 5-volt regulator. Power comes out of the 5-volt regulator, runs underneath and to the input of the Mesa board. We have the encoder inputs from each servo, so X, Y, and Z. We have the step and direction outputs for X, Y, and Z. We have the alarm input for each servo tied in under this wrap where you can't quite see it. And we have the digital outputs to enable the servo and clear alarms that are tied into these terminal blocks back here. Once this is in the machine, we'll figure out the VFD wiring and the homing and zeroing pucks. It's going to be easier to deal with that once it's in the machine so we can test it and we're not moving more stuff around. It's just nowhere near the wiring we already did, so it won't be too big a deal. We should be able to sneak this guy in here. Something like that. And find that hole. Got a Z, Y, X. Shouldn't need that to get in there anymore. Check out how they heat shrunk the label over the ferrule. That can be a problem and has actually caused some notable incidents lately. So just interesting to see that same workmanship issue here. We're going to do a quick test here. If I turn on the machine, we should see LEDs on the Mesa board. It woke up, so we got power. That all looks good. Next thing we need to do is figure out our Ethernet setup. So this is a Cat6a pass-through. It has a connector on one side. It goes through, has a big nut, and it's got a connector on the other side. It turns out that if we pop out one of these plugs, that's fighting me now that I'm doing it on camera. There we go. So if we pop out that plug, this is going to go right in there. Come right through like that. And we didn't even have to make new holes in the cabinet. Little 2-foot shielded Ethernet. I'll turn off the power before I electrocute myself. I saved you the pain of watching me fish this Ethernet cable through, but we can see it goes through the panel, goes through the chase now, and pops back out at the Mesa board. Since the next thing we're working on is the VFD, I relocated the control panel, which normally comes out the front of the machine. You see it's just got a connector on the back, and there's a wire that ran up to the hole in the front panel. So we're just putting this back here for now, so it's a little bit easier to work and see what the drive is doing while we're looking at wires and all of that. It'll go back up to the front panel when we're done. The big advantage on the Spindle is that we basically turn it on and let it run, and we only need to check if it's getting into an error condition or something. And rather than go with analog signals and some digital outputs to indicate that like it had before, we're just going to run a Modbus RS-485 connection to the Mesa board. So just like the other one, we're going to strip it. We only care about the blue and green wires. So if I read everything right, blue is going to be negative. So we're going to put a blue into pin 14. Not the prettiest thing, because that green ended up too short somehow, but we'll at least test with that. Electrically, that's all we should need to do to get the Spindle working, but it does need quite a bit more configuration both on the Spindle and in LinuxCNC. We want 8N1, which is 6. Transmission speed to 115.2. Modbus enabled. Remember when I said it doesn't matter what firmware we put on the Mesa board? Well, now it does. We need configuration that has packet UART on serial 0, but none of the ones in Mesa CT do. So I had to download the full file from Mesa and found that there is one that does, and it still has the step and direction and encoders that we need. But now we have to use Mesa Flash to do that from the command line instead of using Mesa CT to do it. Okay, I finally got this incantation right after trying a bunch of times and then finally just looking at the forum. Now we should be able to write a configuration file for Mesa Modbus to tell it what registers we need to read and write from the VFD. If everything's working, we should see the fault status be false. But of course, nothing could be that easy. So I found one mistake. There's 2 versions of serial Modbus, RTU or ASCII. We want RTU. But I accidentally set this to 6, which is ASCII. We want 12, which is 8N1 RTU. And the fault went false, so that's working now. We have Mesa Modbus talking, but we need to actually do something with that data. And Mesa Modbus can do a little bit of parsing and massaging of the data from the Modbus registers, but it can't deal with this, which is a complex bit-packed field. For each one of these registers, I wrote a HAL component which parses that data and makes it available in easier formats to consume by the rest of LinuxCNC. Going to load those components and connect them to Mesa Modbus and connect them to the Spindle component so it responds when the G-code runs. But wait, there's more. We still have to tell the VFD to accept those commands over Modbus. And then as a safety feature, we're going to configure it to automatically shut down if it hasn't heard a Modbus message in more than 2 seconds. So what's going on is if I come over here, I can enable the spindle, and the buttons aren't working. But if I run this, I do have a spindle running. We can see 3000 RPM, and it's over here spinning. If I try to run it counterclockwise, I get nothing. I knew this had to be in here. So there's a setting, 0023, which if it's set to 1, disables reverse. We actually already see that it's working because it says reverse. So now if I turn it on forward, we're going forward, stop, go in reverse, and we're running in reverse. Awesome. And now it's time to rip out all the old analog control cables. So, should be able to start fishing this out. Hopefully it's not too tangled in with other things. What is this yellow guy? Now where does he go? So we yank that. What is M11 going to a relay for? I don't know what these wires would be. Every one of the screws in here was put on by somebody with some anger management problems, I think. Because they're just at the edge of stripping out. I still got one more wire in here, and it's going somewhere. That is a big ball of servo control wires. That's the spindle wiring buttoned up, but now we need to do the homing switches before we can actually give this machine a full test run. This is the X-axis homing switch. It's on the carriage, and if I bring that over until it gets near that little metal plate, you'll see the light come on as it detects it. We're going to go look at the other end of this and compare voltages and things to see how these switches are actually behaving so we know how to hook them up to the controller. Z is off, Y is off, X has 55 ohms. Looks like they're just tying to ground. So we'll set up for 4 pairs of inputs. Up here on these, we'll wire those to 5 volts. We'll pull that off of the stepper step direction header, just like we pulled a ground for these inputs. And we found something labeled in English. That's awesome. It doesn't really matter how we wire these, so I'm just going to pick up an order that makes sense to me and go with it. So starting from input 0, we're going to go X home, X limit. And then we'll do Y home and Y limit. Then we'll do Z home and tool setter. The A home, which again we don't even have the fourth axis, but we might as well hook it up. And X11, which I'm 90% sure is E-stop. All right, so that's our little harness. Just got to get that up in there now. And now more LinuxCNC configuration. We need to configure the home and limit switches for each axis. The Z-axis doesn't have a limit switch, only a home, so there's only that. Then for the Z probe, the tool setter, I put that in its own file. That's going to get a lot more complicated later, not in this video. So that went in its own file, and then had to configure the homing cycle in the init file. The big piece there is the speeds, so it doesn't ram into things. And that the Z-axis needs to home first, so if it's down and would collide with something, it comes all the way up, and then it homes X and Y. The last bit of not quite homing is the Z puck. So the bit comes down and touches that and tells the machine where the end of the bit is relative to the top of the workpiece or the fixture or whatever you put the puck on. That's supposed to work like a switch. So there's continuity from the bit up through the spindle, through the bearings, into the chassis of the machine. And the puck is connected to one of the digital inputs on the controller. But we got a little problem here, and that's not working. So there's no continuity right now from earth ground to DC common. And then there's still no continuity from DC common to the 5-volt negative that powers the Mesa board. On the RichAuto board, the input negative is connected to the chassis of the board, so that was connecting those two. But we don't have that, so we need to add a wire from the DC common to earth ground, and also a wire from the 5-volt negative to DC common. The Mesa board also has a dedicated earth ground that is not connected to its DC ground input, but we need to connect that back to earth ground. So then, moment of truth, does anything explode? No. That's good. You can do a little test, touching the puck to a ground, and we can see the input indicator light is turning on and off. So that means all of our grounding is good now. Ooh, wildlife. Okay, back from our distraction. I had some settings with the z-axis wrong. It was inverted. We want positive to be up, negative to be down. So we had to tell it that when it's homed, it's at 190 millimeters, and then we should be able to test a homing cycle, and that's not what it was supposed to do, but that's what we put the puck on something soft. Turns out I had those settings wrong, so you have to tell it it's at 190 and then to stay at 190. And that looks a lot better. So now to the forums to figure out how to set up the Z-probe itself. This time Waldemar had some good information on how to get that configured. Went ahead and copied the bulk of that over, including a PyVCP setting to add a button to run that. And we can see it run. It's very slow. There it goes. All right, we'll tweak some settings to speed that up a little bit, but it's time to do a thing. Alright, I'll call that a success, but I haven't put everything away because there's another step to this project. We have a tool changer that we need to get hooked up, but that's going to be in the next video, so stick around.